Hello everyone, welcome to Aircraft Structures Lab course. My name is Puneet and I am a research scholar in IIT Bombay Aerospace Department. Today I will be showing you a vibration experiment. So in this experiment, our aim will be to determine the Young's modulus of a material using the natural frequency of that material. So in this experiment, we will be measuring the natural frequency of the material, and using the natural frequency, we will use the course content, the vibration course content that we have learned, and we will be determining the Young's modulus to the formulation that we have learned in the due course of a semester. So I hope you all have went through the structural dynamics course in your previous semester. So you all have learned that vibration is a back and forth movement of a body about its equilibrium position under absence of external forces, but under the presence of internal restoring forces. So we all know that when a body is disturbed from its equilibrium position, it vibrates at its natural frequency, and the number of natural frequency for a body is dependent on the degrees of freedom of the corresponding system. Here we will be using a steel scale which acts as a cantilever beam. So in this system, it's a continuous beam, so it has infinite degrees of freedom, and correspondingly we will be having infinite natural frequencies and the corresponding shapes which are called as the modes. So we have here in this slide I have shown 3 modes for a cantilever beam. So similarly, we can have infinite number of modes and natural frequencies for a beam, but to exert higher natural frequencies we need to provide higher energy. So in order to avoid this, we are exerting just the first mode or the first natural frequency of the cantilever beam, and we will be using the first natural frequency to calculate the Young's modulus of the beam. So here you can see that the first mode consists of the first mode does not have any nodes in the equilibrium position, and the second mode has one node at an equilibrium position. Similarly, the third mode has 2 nodes at the equilibrium position. So the number of nodes at an equilibrium position defines the mode number of an elastic body. So in this experiment, we are using a steel scale as a cantilever beam to excite it to its first frequency and calculate the Young's modulus of the steel. So here we will be adding an additional weights at the end of the beam. The reason why we are adding additional weights of the end of the beam is to bring down the natural frequency of the slender cantilever beam. Otherwise, it will be difficult for us to note down the time required to complete the number of oscillations of the elastic beam. So that is why we will be adding an additional weight at the end of the beam just to bring down the natural frequency. So in that case, we can neglect the weight of the steel beam. In this case, the steel beam is a scale or a steel scale that we have considered. So considering a massless beam with an end or a tip mass, the natural frequency of such a system is given by the formula omega n is equal to 1 by 2 pi into under root of 3 EI by ml cube. So here L effective is the effective length of the beam, which will be further explaining in the experiment. E is the Young's modulus, I is the moment of inertia about the bending axis, m is the mass of the beam. So rearranging this equation, we can write E in terms of the natural frequencies, mass, and the effective length and the moment of inertia. So in the experiment, we will be noting down the time required by an elastic axis or elastic beam to complete n oscillations. So that n and t from the experiments or from the experimental observation will be used to find the natural frequency omega n. And once we have the natural frequency, we can back substitute the value of natural frequency in the formula of Young's modulus to find the Young's modulus of the steel. So here in the experiment, after the experiment, you will have to calculate the natural frequency of the beam once by considering the mass of the beam as well as once by neglecting the mass of the beam. So by considering the mass of the beam, the effective end mass or the effective mass of the beam at the tip is given by this formula over here, which is mb is equal to 33 by 140 into rho L effective. So this again can be calculated with the data that will be shared with you. So, the equipments that we will be using in this experiments are bench wise, elastic steel scale, weights, vernier caliper, stop clock and a weighing scale. So, in this experiment we will be using this scale to perform the vibration experiment, and to start off with we need the width and thickness of the scale, which we will be measuring using a vernier caliper, and also along with that, to find the effective length we will be measuring the width of the weight that is shown here, and other than the width we need the weight of the weighing that will be attached to the scale. So, we will be weighing the weight with the help of a weighing scale that is shown here. So, this is the experimental setup for a cantilever beam. So, we have used bench wise to set up elastic steel scale as a cantilever beam, fixing the scale at one end using a bench wise, and we have attached a mass at the end, as I have explained earlier, to reduce the natural frequency of the steel scale, which is which has a very high frequency without attaching the mass. So, the effective length of this cantilever beam is from the fixed end over here to the middle of the weight. So, that is why we require the width of the weight that has been earlier measured using vernier caliper. And now, in this experiment we will be disturbing the beam initially from its equilibrium position, and we will be measuring the time required to complete 20 cycles. Okay. So, using this using the time measurement, we will calculate the frequency of this beam with added weight. So, initially we will be disturbing start 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And we have measured the time that is required for 20 cycles to complete, and we had measured that it needed 20 seconds to complete this 20 cycles. So, using this time we can calculate the natural frequency, and using that natural frequency we can calculate the Young's modulus as explained in the earlier slides. So, similarly we will be repeating these experiments for different weights and also for different trials, and we will be repeating it so that we reduce the error in the experiment, and we will be calculating the average Young's modulus from this experiment. So, we will be repeating these experiments with different weights, like here we have used 4 weights, and we will also be repeating with 6 weights, and we will be noting down the oscillations or the time that is required to complete 20 oscillations, and using the time we will use it in the natural frequency formula to calculate the Young's modulus. So, we have measured all the length parameters and the time taken and the time needed for 20 oscillations for the steel cantilever beam. So, we will be sharing all this data with you for the further calculations. So, once you have all the time parameters, density of the scale, and as well as the length parameters, you can use all these parameters into the formulations that was discussed in the previous slides, and you can find the Young's modulus and tabulate it for different values of weights and for different trials. And further, your task will be to find the Young's modulus of the steel, and also to find the Young's modulus of the steel by considering the weight of the beam, which is a steel scale here, and also to find the error between considering the weight and without considering that. What is the error that you get in the Young's modulus? You have to tabulate that as well, and also answer the questions that has been shared in the lab manual with you. Yes, thank you.